Good evening, everybody. As you might have noticed, we have a fair number of, looks like new people here tonight. But for the old timers, obviously, I'm not Claude. So anyway, for the last 2 years, you've been seeing Claude standing up here, emceeing the meeting, hosting the meetings and all that. Claude was the outgoing president from last year, and I am the incoming president. So this is my first night to be doing this. So we'll see how this goes. And naturally, it's probably the biggest meeting we've had in a while. And it's my first night. So I always love that. So anyway, we have a lot planned tonight. So let's get to it here. My name is Steve Bradshaw, by the way. I am the club president as of a couple of weeks back, or 3 weeks ago now. So anyway, this is tonight's agenda, so you can get an idea of where we're heading over the next couple hours. So we have the meeting called to order, which we just did. It's now been called to order. We'll have a welcome here in just a moment. We'll have about 5 or 6 minutes of announcements, pretty standard stuff that we typically always do. Then we have an observing award tonight. So if someone has done some work in the sky and they're going to get recognized for that tonight, we'll have an observing award. We're also going to have is Jake Lealcala here? Oh, there we go. I hadn't seen you yet. So anyway, we are going to also introduce our new events coordinator a little bit later on tonight. So nothing super formal. Jake will just come up here and kind of introduce himself, put a face to a name and say a few things. He'll do a longer presentation probably next month. And then we have a member presentation tonight as well. And that'll probably take 10, 15 minutes or so, I would imagine. And then we'll do our 7th inning stretch, give everybody a chance to kind of stretch, run to the bathroom one last time, get that last ice cube in your drink cup or whatever. And then we'll have our main presentation night, which is Dr. Adler, who's back in the room there. And he's, as you can see, is going to be talking a little bit about the geology of Mars tonight, which I actually am very excited about. With all the things roaming around on Mars these days or flying over Mars these days, we're getting so much information about it that it's just actually quite intriguing to me. So I'm very much looking forward to your presentation. So anyway, let's get to it here tonight. And first of all, welcome to everybody. So we're happy to have you here tonight. That extends to not only the people here in the room, which is there are significant people in the room, but also the people that are joining us via Zoom. So welcome to everybody. We thank you for being here. The goals for tonight, we hope you enjoy yourself. So there's number one. We hope you learn something. So there's goal number 2. We hope you make a new friend. And we hope you also reconnect with some old friends here tonight. So there's kind of the goals for the evening, okay? So hopefully have a good time, meet with friends, learn something new. First of all, we want to ask if there's any visitors tonight. This is the part where we don't embarrass you, but we do like to know if there's some visitors here tonight. Looks like we have a fair number. So what we're going to do is we have a microphone here, and we're going to hand you a mic. And it's very simple. What's your name? How did you find out about us? What reason brought you here? What intrigued you? What brought you here? What's your astronomy experience? That might be 0, and that might mean you're a working astronomer. You could be anywhere in between those two extremes. And then, of course, if you have something favorite that you like about space or in space or whatever, we'd like to know that as well. So anyway, let's start talking to our visitors here.
My name is Beth. I've been here before, but I haven't been here for 6 months because I broke my wrist. So I'm back and glad to be back.
My name is Barbara. I live in Fountain Hills, and I'm just kind of interested in this since we're going to get a new observatory in Fountain Hills and dark skies up there. So that's why I'm here. Bye.
That's awesome.
Yeah, my name is Mike Wins. Whoa. I recently moved here about a year ago with my wife, although I'm actually only in town half time. I actually found out by guys by Googling you, found you on the web. I was looking for astronomy clubs. I actually work in astronomy. I actually work on the Hubble Space Telescope. That's actually what, in fact, I need to talk to you guys. If you want a speaker, I have something I can tell you about. I've been working on the telescope for 31 years. I'm in the operations area, and so we run the telescope. I actually take care of the fine guidance sensors, which point the telescope. and do that. I'm a systems engineer up there. And so I have to spend half my year over on the East Coast at Goddard Space Flight Facility taking care of the telescope, but at least get to spend half the time out here. The astronomy experience, and so I've been working on Hubble for 31 years. I've been doing amateur astronomy probably for 55 years. I actually started in high school, actually junior high. I had an 8th grade earth science teacher who got me interested, which a lot of us had started up there, and I've been doing astronomy ever since in various places around the country, and so I also, yes, my day job is working on the Hubble, but I actually do a solar observations. I do high resolution prominence imagery because I have my own telescope and stuff, and so I do that. So I wanted to see what you guys were about and to offer, to let you guys know that if you need, I think I can fit one of your dates. I'm actually in town for speaking, because I can tell you a lot of stuff about Hubble you've never heard.
Cool, thank you. Maybe we could borrow your telescope one of these nights, huh?
I think Woody, our vice president, lines up speakers. When you say you might have a speaker, I think I saw him salivate a little bit because he's really excited to hear that.
Hi, my name is Rhonda. I actually went to ASU with their astrophysics program. Left after a couple of years because I decided education was more my track. I was that 8th grade earth science teacher for a couple of years over the pandemic. And my husband and I met in that program, and we're just kind of missing being part of the astronomy community. So when we were looking at what opportunities there were outside of being a researcher at ASU, we found you guys here. So hi.
Hi, everyone. I'm Greg. I'm Rhonda's husband. And that's quite a lot of feedback. At any case, I also went to ASU and about 2-3 years back got a PhD in astrophysics and got a little burnt out by grad school and have sort of moved away from astronomy. And like she said, we're kind of hoping to get back into it. So I'm excited to be back here tonight. A lot of the stuff I worked on for my dissertation was supernova explosions and cosmic neutrinos, that sort of thing. So those are probably still some of my favorite things about outer space.
Thanks, Greg. Rhonda?
Hi, I'm Ed Flynn. I'm visiting from one of the hottest places on Earth, Chandler, Arizona. And I found out about you guys from your website, and I'm an amateur astronomer. I have some equipment. I've tried my hand in astrophotography. I've been a huge APOG fan for about 25 years. So you guys at Hubble, thanks for the memories. And what's my favorite thing about space? Just the sheer size of it. It's incomprehensible.
Thank you.
Hello, everybody. My name is Chandra, and I'm from Canada. I spend my winters in sunny Arizona, Phoenix, and I'm a guest of my friend of long time, Robert Long, sitting right beside me. And I've spent my entire career has been in the world of space. And I'm now trying to probe the world of black holes. So one of these days, I may put something together. So Astronomy Club was the obvious place to visit here, and I'm glad to be here.
Great, thank you. Welcome. I think Lavi was one of our youngest attendees before, but I think you might have competition today.
Good evening. My name is Terry. I'm here with my wife Ann and my daughter Betsy. Years ago, I had a telescope. We moved, we lost the scope. I've forgotten everything I ever learned about astronomy. And then my daughter told me they had an observatory here 4 weeks ago now. And that's what brought me here. I'm also the guy who was posting on the forum about, or the Facebook, about the meager little 70mm telescope looking at the moon.
Great.
Anybody else?
Say a few words. Okay, I think that's it then.
Welcome to our new visitors. We're glad to have you here tonight. Hopefully you have a nice, enjoyable evening. Hopefully you enjoyed Dr. Adler's presentation on Mars. Like I said, I'm very much looking forward to it. All right, we have a few just sort of standard announcements. This will take about 5 minutes probably, and then we can move on to some of the other things we need to do. These announcements will be similar pretty much every week, the first several slides, just to give everybody, obviously we have a lot of new people tonight. How do they get involved? How do they find out what's going on? That's what the next several slides are going to be about. So first of all, I went out and I took a screenshot of some of the slides on our website. So, and anything you see in red, I've sort of superimposed over the slide. So that's actually not part of the web page exactly. It's just notes I've added to the cell. So we do have a website. If you go out to the website and you'll notice I've highlighted the join page. So if you click on join over there, it gives you at least 3 different ways you can join our club if you'd like to do so. Notice there's PayPal is available, so you can do that online if you'd like. You can also use mail to join our club. So that's an option on the website as well. Or since you're here, or you might be here next week or whatever, in the back, on the back table back there, we have Brooks Schofield, who's our treasurer. He can certainly take your money and get you signed up as a member and stuff tonight as well. And so if you become a member, what does that mean? What do you do with it? Where do you go next? All that sort of stuff. Well, pretty much at the bottom of any of the web pages on our website, there is a link or a set of links at the bottom, one of which is this new member guide. So if you click that new member guide link at the bottom of any one of the web pages on our website, it'll bring up this little PDF and it goes through all the different things you can do and what's available to you and how you get involved and all that sort of stuff. So that is available to you should you be curious on how to do that. So just want to make sure you know about that. Once you've joined or become a member of the club or whatever else, then the next thing is going to be, well, what's happening at EVAC? How do I join the fun? What is the fun? How do you do all that sort of stuff? Well, actually out there on our website, again, if you go over to the home page, so I've just highlighted it there for you, scroll down a bit, you'll see a subscribe link. So you can subscribe to a mail list called EVAC Announce. And anything that's happening, we pretty much make an announcement about it and it goes out on that mail list. If you'd like to sign up and subscribe for that, you can do it right here on this website. It'll walk you right through it. Couple things you should be aware, it's not going to be a giant spam factory for you. I probably get half a dozen emails in any given month from the club. So it's not going to be like you're getting an email every other day and you got to control that. And also we don't send that distribution list anywhere else. So it's not like we're going to sell off your information and put you on 50 other mailing lists. So anyway, it's just for us. So that's a good way to just have events or information pushed to you automatically. So you're just aware of them. If you really don't like to do the email thing, you can always go over to our website and go to events and meetings. And on that, there is a calendar, and anything that's going on that month will show up on the calendar. And you can click on the day, wherever that event is, and it'll bring up the details of the event. It's just another way to stay involved, stay up to date on what's happening, what you might want to participate in, things like that. There's a third place you can get information about what's happening with the club. And that's going under news and resources, that page. And out there, there is a newsletter link. And you can actually see a newsletter every single month. So it'd be information, various things that's happening just that particular month. And actually the history of all the newsletters out there as well. So you can look at what we've done for the last few years if you really wanted to do so. So there's different ways you can find out what's happening at EVAC here at the East Valley Astronomy Club. You have the equipment to join the fun. If you'd like to have some equipment and you don't have any, we also have some ways to do that. Also on the home page of our website, if you scroll down a bit, there's a section there called astronomical equipment. Notice there's 2 links there. One is used equipment for sale, and another one is equipment for rent. So our properties manager, Mr. James Yoder, right here, he pretty much manages this part of the club for us. And he's always getting equipment through various ways and methods and means. And he goes through that equipment, checks it out, checks the eyepieces, checks the mirrors, checks the electronics, all that kind of stuff. Refurbs occasionally here and there a little bit, or repairs a little bit. And then we sell that equipment at really drastically reduced prices. So if you're looking for some gear and don't maybe have quite as much money as you might want to buy that gear, you might check with James and see what we have at any given time. He just sold actually last week, a really nice 8-inch SCT. And so someone got a great deal on that. So it's a good way to get equipment. If you're not ready to pull the trigger yet, for equipment, you can always rent as well. And so James handles that for us as well. We have a number of scopes we rent out for a week at a time, or 2 weeks at a time, or 3 weeks at a time, whatever you make those arrangements with him. And that gives you a chance to kind of explore with a telescope and decide whether you want to purchase or not. So that's available to you as well. If you don't know how to use a telescope, or you're a little rusty on your astronomy and all that, we also, underneath the news and resources page on our website, have a virtual beginners lab, and every one of those blue boxes is a link, and it opens up a web page, not a web page, but really almost a PDF. It is a web page, so it's a PDF that walks you through some aspect of the telescopes or astronomy or things like that, where you can kind of learn a little bit about the hobby, the science, and everything around astronomy. If, per chance, you're more of a hands-on person and you want to interact with an instructor, a few times a year, we actually have hands-on classes as well. Once again, our properties manager, Mr. James Yoder, teaches those classes. And notice we have 2 different classes. We have sort of a basic telescope operation class, and we have a planetary astrophotography. The classes are actually over Zoom, so they're really easy to attend. But then on Saturdays, they have, usually Saturdays, they have telescope hands-on as part of the class as well. So it runs a few weeks, and so James does that. If you're interested at all, because James is our properties manager for the club, he has an email alias that goes to him, which is properties@evaconline.org. And if you're interested in that, let him know, because once he gets 3, 4, or 5 people that are interested, then he'll usually pull a trigger and run a class. And you can go ahead and join that if you'd like. So this is how you get more knowledge. Now, once you have, you're with the club, you know what's going on, you have the knowledge, you have the equipment, how do you get involved? It'd be the next thing here. We have 2 primary methods to get involved and give back to the community. We do have an observatory that we operate here on behalf of the city. It has a long name, as you can see, 14 syllables, I've counted. That's why we just usually call it Greco, because no one wants to do the 14-syllable long name. So anyway, it's all of a 4-minute walk out this direction, and it's open tonight. Matter of fact, our couple guys are over there running it right now. You can see the details of when it's open to the public and stuff. It's a great way to get involved. And if you'd like to get involved, you can email the address I have up there on the slide. And all that does is it puts you on an email list. And what'll happen is at the end of every month, usually Claude, who runs the observatory, will send out an email to everybody. Do you want to work next month? And what nights are you available? Or which nights are you not available? And you tell Claude that, and he figures out a schedule, and then you're usually scheduled 1 night through sometime that month is to work. And it's you can see the hours and all that. It's just a great way to get involved. Okay. Also, second Friday of each month, which happened to be last Friday, we have members star party out there as well. So if you want to bring your telescope and set up in the grass outside the observatory, you can show your telescope to other people, let them look through it. You can point at whatever you want to point to, show other people how the sky as well. And it's just a great way to kind of give back, get involved, and do things like that. The other primary method of getting involved is to go and help support the private star parties that we do for schools and community centers, HOAs, science centers, things like that. Once again, there is an email address there. You can go ahead and say, hey, I'd like to get involved with this. It'll actually go to our events coordinators where that'll go. And he'll do the same thing as we get booked into a school or an HOA or a community center or whatever else. He'll say, look, we have an opportunity for a star party. Who would like to do it? And if you're available, you go. If you're not available, you don't go. It's that simple. So, and usually it's about a 3-hour commitment. I do a lot of them myself. I think they're fun. It's usually 2 hours there, and then you got your commute at each end and about 20 minutes to set up when you get there. So it's usually about a 3-hour commitment. We do it primarily just here in the Southeast Valley. We try not to go out to Globe or Maricopa or anything too far away. Occasionally we do, but some of the more regulars usually handle the longer trips. Most of it's right around here. One I happen to love is the American Leadership Academy. It's 5 minutes from my house. I love that one. 5 minutes away. Perfect. So anyway, why do you want to do this? That's why. Because if you look, it just feels good to give back. You've all given a gift to somebody at Christmas or a birthday, and they just love the gift and they're excited about what you did, and you feel good for giving them a gift. And that's what we're doing when we go out to the community and give them the gift of the sky. So it just makes you feel better. Plus, you're going to learn more about the sky and telescope operation by just being out there doing it. So that's another benefit. And also, you're going to build friendships. By getting involved in these smaller group activities, you get a chance to talk to other members, build bonds, relationships, things like that. I'll give you a good example. There's a guy named Steve sitting right back there in the audience, and Steve and I met about a year ago at Greco at a volunteer event, and him and I are good friends now. Like, we went out Christmas Eve to the desert together, and we're looking at the sky together. So it's just a great way to meet people is what it is. So if you're happy to have this club, last sort of standard announcement here, there's a number of people that you can thank along the way, somewhere along tonight or a future night. First of all, Woody Sims is our vice president. So he's the one that sources all of his hands up right there. He's the one that sources all of our speakers every week. He's the one that salivated when the gentleman over there said, hey, I might have a speaker. So anyway, he does that. And he's also sends out reminders for us. So he does a lot of good work for us. Brooks Schofield is in the back. A lot of you dealt with, he had a long line back there tonight. So a lot of you dealt with him. He does all our treasury stuff. Great job. I just spent a few hours at his house a couple Sundays ago going through a stack of papers this high of all the financial stuff for 2023. And he does a wonderful job of keeping track of all that for us and keeping track of our membership roles as well. We also have James Yoder. Mr. Renaissance Man does it all. So he's a properties manager, the secretary, the class teacher. He helps with the AV. He does a little bit of everything for us. So James is up here as well. Brandon Felden, I see him tonight. He might or may not be here. I didn't see him, but anyway, oh, he's at the observatory tonight. I was going to say, I didn't see him in the room. Anyway, he's our web guy. He does a great job. I know something was a little outdated last week. I sent him an email, and within 2 hours, it was fixed. So he's just really on the spot with that. Marty Paisanka, he does our newsletter each month. Marty's been around a long time, done a lot of things for the club, but now he's doing our newsletters for us. So he's involved as well. And then you'll meet Jake in just a few minutes. He's going to be up here to say just a few introductory words. He's our new events coordinator, handles some of this public outreach stuff for us. And all of these people, if you want to communicate anything to them, suggestions, input, thank yous, whatever that might be, all of these people have email aliases, and those aliases are on our website. You can look them up. You can email James, the property manager, or Woody, the VP, or whatever, and it's all listed on our website. And as always, we do have a board as well. You can see the various board members there. A couple of people are in the room here tonight. Tom's right here at the front, and then I think Nathan's in the back over there. He's one of the board members. Claude's over at the observatory. Don had sort of an issue. He couldn't be here tonight, and I didn't see Alex. Is Alex in the room? Okay, didn't see Alex, but anyway, these are our board members, very experienced people, kind of provide good guidance for the club. All right, that's it. So we do have an observing reward now. So Wayne, where'd you go? I saw you earlier. There's Wayne. I'm going to give the mic to Wayne, and he's going to present an observing award to one of our members.
Thank you. It's my pleasure as the observing program coordinator to hand out awards when somebody completes an observing program. We have several observing programs that you can look for on our website. The ones tonight go to Nathan Eskey. So Nathan has observed 2 of our lunar programs, the Lunar Program Observing Program and the Lunar 100 Observing Program.
Yeah, thank you.
So congratulations, Nathan. Thank you.
All right, congratulations for that, Nathan. And you're going to learn about a little bit of what he learned, because he's our member presentation night, and he's going to talk about some of the things he learned as he went through this observing program. So you'll be hearing from Nathan here shortly. Another thing we're going to do, Jake, if you want to start making your way up here, we have, over the last year, Claude, our old outgoing president, actually wore 2 hats. He was the president of the club, but he also was doing all our events he coordination. So all the public and private star parties that we sort of manage and attend and staff. Claude did all that as well as being president. Jake is offered to step up this year and be our events coordinator. And he'll be presenting a little bit more formally next month, but he just wanted to say hi, put a name to a face. So Jake.
How's everybody doing? My name is Jake Lealcala. I joined this club about 6.5 months ago in July. Figured, what the heck, I got a couple new telescopes, might want to meet a couple new people and see what it's all about. And I always wanted to go out and do some star parties with large groups, and this was kind of the right spot for me, I guess. And a little down the line, I got to talking to Steve and Claude and just thought, well, if they need any help, I've got a lot of free time, so I might as well give myself up to help out and do whatever I could. So, and I'll be around if anybody has any questions about upcoming events, or if they know of an organization that wants to schedule an event. We do all kinds of star parties with, like Steve was saying earlier, with schools and other organizations. So looking forward to it. Thank you, Steve.
Thank you, Jake. Yeah, hopefully Claude is enjoying a much appreciated and well-earned rest. He's done a lot of things for the club over the last couple of years, so I'm sure he likes having a little bit less on his plate for a while. Although he's off meteor shopping and doing other things lately here as well, so he's never going away. Anyway, we have a member presentation at this point. So Nathan, if you want to start heading this direction up here. Obviously, he just got an observing award for some of the work he's done observing things on the moon. So he's actually going to walk us through a short member presentation about some of the things he discovered and learned and found along the way. So anyway, this is your first slide, Jake.
Yeah, thank you. So hi, I'm Nathan Eskey, and this is going to be more of a beginner or a presentation. So I wasn't aware that some of our visitors would have the Hubble Space Telescope, but since we have an atmosphere, hopefully even you will have some things to learn here. As was already mentioned, we do have some observing programs, and to me, the moon is very obvious in the sky, but it's one of the most interesting objects to look at. It has a very low barrier of entry, so you can use binoculars or, for some of the features, just your eyes. And the two programs that are just simply fantastic. And instead of just grabbing your telescope and say, look, there's the moon, these programs essentially take you on a tour. All of these features are up there that I was just simply unaware of. So in total, there are about 190 features on the moon that these two programs call out, and there's very little duplication between the two. And what's really great about these programs is it tells you when the best time to view these features are. So depending how far the moon is in its lunar cycle is how old it is or how many days. And these programs thankfully tell you exactly how many days to a particular feature is available for you to view. Each of the observation programs provide you with a log form, observation, where you can print it and simply write the dates, the location, the telescope you used, etc. And that's really all it takes. I took an extra step to convert it into an Excel spreadsheet, so I was able to weed out a very few of the duplicates that are there. But the reason I went this way was for the filtering, really. So, I'm a busy person. I'm not retired yet, which I really want to be, but I take my telescope out when a opportunity presents, and so I just quickly look to see how old the moon is in its cycle, and I just filter it. Let's say it's 9 days old, and I can just filter to see what type of targets that I should look for. In terms of equipment, like I said, you can use binoculars. It's really, really easy, low barrier of entry. I have a Celestron 8-inch SET telescope. It's an 8-inch. And for me, moon filters were a necessity. You can imagine, having an 8-inch wide eye looking at the moon. It is incredibly bright. So I had two moon filters, a 13 and an 18-inch, and I think those are a must-have. My favorite accessory on this picture is actually my little camping chair there. I like to have my telescope very low to the ground, and I can then just sit and enjoy it and not hurt my back. And then additionally, I wanted to play around with some astrophotography, or rather lunar photography. And this is where my presentation switches slightly over into that particular era. Here's a close-up of my eyepieces and my filters and my camera. So with all this, equipment, I thought that I was ready and like I can just jump right in here and get some great pictures of the moon. And then this is what I ended up with. I was so disappointed, so heartbroken. And this is where the EVAC, the virtual classrooms really helped me. And on this picture, I don't even know what I'm looking at. I know it's blurry. If you look in the corners, that little black area, that means my tracking was bad. So I expected more. And so I wanted to break it down into two problems I wanted to solve. First was, what am I even looking at? And the second was figuring out why my image was so bad. So I dug into the first problem, what am I looking at? And here I downloaded the Moon Globe app, which is a favorite of my apps. And I was able, using the settings, to switch the moon left to right because I'm using a Smith-Cassegrain, so it's mirrored for me. I was able to zoom in and essentially see what my eyepiece would have seen. So I can, look at my eyepiece and then look at the app and then figure out what I'm looking at this way. The problem is that there wasn't any search functionality. Another app that I used was Starry Night that came free with my telescope. This one has basically all the features as well. You zoom in here to a great degree. Excellent detail, but as you can see, it's more of a radar image instead of what you actually see in the telescope. So this one was a little bit harder. It did have nearly everything, but it was harder to go from this app to my telescope to figure out what I was actually looking at. And again, no search functionality. And then finally, I found the Moon Wiki. And here I finally have a search where I can type in a crater's name or something like that, and it can tell me where it's located, either by telling me what mare it's in or by saying it's northwest of another large crater. And I ended up searching this Moon Wiki even for things that I could find pretty easily, because this not only tells me where it is, but it provides the historical and the scientific context of why I'm looking at it. And this really changed the observation programs for me from just a checklist and more of a journey, more of an education. Why is this important? And this Moon Wiki really helped fill those gaps for me. And then I also learned about transparency, which the Hubble does not have to deal with, I don't think. So this is more why my image was kind of bad. So it's basic astrophotography concepts. Transparency is basically, is the sky clear? Using your naked eye, is there anything in the way, whether that's light pollution or clouds, that's prohibiting you to see things? Next is seeing, the concept of seeing, I should say. And that's really is what you're seeing, is that shaky or crisp? So you can think about this, or at least I think about it as sky turbulence. What is the atmosphere doing up there? Is it super windy or is it nice and calm? And that ended up playing a big difference for me as well. Then I also wanted to figure out what type of magnification I was getting with my camera. I was not able to find a zoom out for it. So at astronomytools.com, I was able to enter my telescope and then my camera, and it produced these nice rectangles with what my camera can do by itself and then with a Barlow lens. It didn't provide me exactly what I was looking for, so I overlaid some eyepieces that I have. So my camera itself is roughly equivalent to my 5mm eyepiece, and that gives me a magnification of 406, and then with a Barlow, that's going to be over 800. So that's essentially one of the problems I had, is that each telescope, based on its size or its focal length, has a useful level of magnification. And so my telescope tops out at 480. So anything higher than that, and it really becomes increasingly difficult to focus. Additionally, the seeing was really bad when I was viewing the moon about only 20 to 30 degrees above the horizon, which I learned is absolutely terrible. The best time you want to view things is when it's straight overhead, or what's called the zenith. When it's as high above the horizon as possible, you're going to have the less atmosphere, the less weather conditions that you have to deal with, and will really improve your picture. And then for imaging, I spent some time trying to learn software. So I ended up trying 3 and ended up sticking with ASCII-Cap, which was recommended and came free with my camera. And then once you have those pictures, depending on your camera, it'll either take a video or it'll take basically a stack of pictures that you have to basically merge together. And so for image processing, I had to figure out how to do all these settings, and I still don't know. So maybe James, I will be talking about you in a class in the future here. But I was able to get some basics down here. So ultimately, with my research and preparedness and knowledge, I was able to go from this picture to this one. So much better. So does anybody want to raise their hands and guess what's this large crater in the middle? If Don was here, he would get it right off the bat. All right. So there we have Clavis. And what really impresses me here is that you can see the craters that are overlaying each other, that would determine how old they are. And then we have another one here, and this is more of the Mare Imbrium. And you can see kind of the color variations coming off Aristilis over there on the right side. And then here we're looking at the terminator, which is basically the line between the light and shadow of the moon. And that's the best place to look for detail and variation. And so here, looking at the Mar, you can really see which are really the older craters, like Keys right in the middle. The Mare has kind of filled it in. It's absolutely beautiful. And over in Mare Humerium, not sure if it's showing up on the projector, but you can see a lot of the ridges are really, it's wonderful. And then here's another close look. And when you look at the terminator, you can see those mountain ranges. And like, those are the Alps. I can see the Alps from Mesa, Arizona. And then we have a nice valley and the Caucasus Mountains, and the definition, I was just very pleased. But of course I wanted to go further. So let's bring out that Barlow and go to 800 magnification. So I was really able to get a good look at Copernicus here and get a good look at the ejecta and the little mountain or the peak right in the middle. And then I was finally able to get a lot of detail within Gassendi here, looking at those kind of details within the crater itself. So I got better, thankfully, for a 4-year process. So I want to highly recommend the lunar observing programs. Like I said, I started this particular journey 4 years ago when I got my first telescope, and it took about 30 observation sessions for me to get through the list. And I got to play with imaging along the way. And finally, just with a little bit of advice, I just want to say again, don't treat it as a checklist. Don't just mark the boxes. I highly recommend going through the journey, reading, using the Moon Wiki to learn about the history, learning about the Rilla, the scientific interest of it. I just found it all very incredibly fascinating. Yeah, and that's it. Yeah, thank you.
Hey, thank you, Nathan. Very interesting stuff. One of these days, I'm going to have to attempt astrophotography. I haven't gone there yet myself, so one of these days. Anyway, this will be our 7th inning stretch. So we're going to have our main speaker here in about 5 minutes.
For tonight's main presentation, we'd like to welcome Dr. Jacob Adler. He is an assistant research professor at Arizona State University. He is a planetary scientist specializing in the geology of the Earth, Mars, and the Moon. Tonight, he's going to be discussing Mars. Specifically, where he's going to be talking about Mars mud flows as seen from both remote sensing equipment on Mars and from lab experiments here on Earth.
Today I'll be talking about Mars mud flows and why laboratory experiments are crucial as they help inform us how to interpret remote sensing images of these features. My past research has spanned several planetary bodies, including the Moon, Mars, Earth, and asteroids. Most of my research relies heavily on remote sensing, including the rare opportunity to investigate planetary surfaces in situ. In my current work, I use complementary techniques, including machine learning, laboratory experiments to simulate planetary environments, and Earth analog research. Many of my contributions have focused on understanding the history of water on Mars, and specifically answering these types of questions. Where do we see evidence of water-rich activity? And how can we differentiate between different aqueous systems from remote sensing images? And what was the total inventory of water in Mars' past? My current efforts focus on understanding how exactly these sediments would behave in extreme planetary environments. And this can better inform us on whether certain water-rich sites are really ideal places to search for signs of life, or where we can best characterize these places throughout the solar system, and how other methods, like lab experiments, for example, can aid in our interpretation of remote sensing images. And this topic is, of course, quite important for our understanding of the history of Mars. For instance, studying water-rich processes and their deposits can help us understand if Mars once had environments that were habitable, or if Mars once had an ocean. And these are all questions that are related to one of the biggest science questions out there. Are we alone in the universe? And could life have emerged in a water-rich environment? In order to investigate water-rich sites that we may never visit in person, or send an in situ robotic mission, we need to be able to use a variety of methods. For example, we should not just use remote sensing, but also field analog research, modeling, machine learning efforts, and even laboratory experiments, because all of these methods together can provide complementary views. If we solely rely on interpretations from remote sensing, we often hit a brick wall, and we must conclude that multiple hypotheses are still under consideration. For example, after years of debate over the Hypanis deposit on Mars, which relied mostly on remote sensing datasets, we still do not know whether this feature is the largest deltaic deposit or if it's an alluvial fan. If it's a delta, it would imply that the entire northern hemisphere of Mars was submerged under an ocean 3.6 billion years ago. But if it's an alluvial fan, it could have formed on land. Similarly, is this feature a mud flow or is it a lava flow? Many flow features have been interpreted as lava flows across the Martian surface, but newer high-resolution images have caused some of these features, like this one, to instead be recognized as a large mud flow. And is this crater caused by an impact, or is it an explosive volcanic crater? So assigning formation hypotheses from satellite images is not an easy task, and we're often still left with some uncertainty. Where would we expect these types of features to form, for example? And in what time periods of Mars history were these processes active? So we have to come to terms with this fact that we know very little about how these features form in these extreme environments on planetary surfaces. So alternative methods like lab experiments are needed to form our framework for understanding what is or isn't possible. The real strength of lab experiments is that we can precisely control the environmental conditions and composition of sediment flows. This picture on the right shows the Mars environment chamber that we use to control the pressure and temperature of our experiments. And by adjusting the experiment parameters, we're able to simulate activity under past conditions and in present Mars conditions. This project is funded by NASA's SSW program, and it will help us better understand the rheology, which is the physics of the flow, and the resulting deposit morphologies, or the shapes left behind that we may see in remote sensing images. When we think of sediment transport on Mars, we see examples that cover a wide parameter space. Sediment transport by liquid water has occurred throughout the different eras of Mars history, and it has spanned atmospheric pressures and surface temperatures, and even water availability and surface chemistry changes. So this is a large parameter space, and we want to ask ourselves, how is sediment transport affected by these parameters? But when we think of the diverse examples, which range from alluvial fans and deltas to mud flows and even mud volcanoes, there are still many outstanding questions. For example, how can we tell a mud flow from a lava flow on other planets? How do mud volcanoes appear on other planets? Are Earth fans suitable analogs for Mars fans? And ultimately, some of these questions we will not know the answers to until we get there and explore these sites in situ. One of the more shocking discoveries in recent years was published by my collaborator Petr Broj in 2020. And to summarize his experimental results, he found that mud flowing over a cold surface on modern-day Mars would behave like Pahoehoe lava on Earth. And here's a video of some of those shocking experiments. So here you're seeing inside the Mars chamber, and on the top you see the same composition of mud as on the bottom, but the top is at Earth pressure and the bottom is at Mars pressure. So notice the remarkably different rheology and deposit morphology. On the bottom you have multiple lobes that form, and they advance in sort of a steamroller fashion where new breakout lobes can emerge and flow over the surface. On the outside of the Martian flows, you have a crust that forms, and this is a frozen icy mud crust. And what that does is it insulates the mud inside so it can stay a liquid, much like a crust on a lava flow would insulate molten lava inside. We also observe other phenomenon like inflation, where the flow can inflate over time due to vesicles or bubbles trapped in the flow. And so some of the dominant processes that we observe are the same as for Pahoehoe lava. We see inflation, lobe formation, this steamroller effect in new breakout lobes, and an insulating crust which keeps the interior molten, or in this case, keeps it mud instead of ice. Now let's think about these same four dominant processes as we look at a Pahoehoe lava flow. So in this video of a lava flow, you can see inflation as crusted areas become more inflated over time. You can see the crust forming, which insulates a molten interior. You see these lobes forming, and when new breakouts occur, you see the steamroller type motion. And here again, you're seeing inflation at the end of this flow. But there's yet another shocking result that we observed in some of Petter's lab experiments. And so to summarize another paper that he published in 2020, essentially, in lab experiments, he observed that mud over a warm Mars surface would levitate and would travel farther than expected. And this was quite shocking because if you think about it, we don't normally think about mud levitating anywhere on Earth or other planets. And so to see evidence of this would indeed be shocking. And so I wanted to investigate, is this really true for modern Mars? And if it is true, what does it mean for ancient sedimentary features? We do know that the current atmospheric pressure on Mars is extremely low, right? The average is about 5 to 7 millibar. Earth, by comparison, is 1 bar, or 1,000 millibar. And so liquid water is not stable on the surface today. However, in the past, Mars was more hydrologically active, and there were muddy streams, debris flows, possibly mud volcanism, shaping parts of the planet, indicating that water was stable for longer time periods on the surface. And so sites with sediment flow features are thus important targets for us to study, because they really probe what the paleoclimate history was like, and especially the amount of water that was active and available on the surface. If we look at these two plots, we see the current surface pressure on Mars. This is a model from Zhang et al. 2012, and also the maximum surface temperature prediction for the surface of Mars. And the importance here is that there's a large parameter space in both pressure and temperature on modern day Mars. And so you might expect different physical conditions, so different styles of sediment flow at different locations on the surface. And this also varies with time. So you might expect the physics of sediment flow to be different during even different seasons, times of day, or times of year. These points can again be illustrated in the following plot. This is a pressure temperature diagram of water. So it shows where the phases of water are stable. And on the y-axis, you see that Mars spans a variety of pressures, as we saw in the previous figure. So at the very bottom, at the lowest elevations of Mars, you have the most atmosphere above it. So if you're in the Hellas Basin, you're -8 kilometers elevation. Whereas if you're at the very top of Olympus Mons, the highest point on Mars, you're 21 kilometers above zero. And so this 29-kilometer span of elevation creates quite a pressure range. And so on average, Mars pressure today ranges from about 1 to 14 millibar. And so to get stable water, you really need the temperatures at the surface to be within a narrow range, especially above 273 Kelvin, which is 0 degrees Celsius. And when we think about Mars history, we actually define the geologic timescales in terms of water and its activity. So the oldest phase of Mars history is called the Noachian. And this ranges from when Mars formed about 4.5 billion years ago up until about 3.7 billion years ago. And during the Noachian era, water was stable at the surface, and we see evidence of rivers and lakes. Then there was this period of climate change on Mars, which we call the Hesperian period. And we see evidence of water being stable during some parts of the Hesperian, and especially outbursts of massive floods, and even the water table and underground aquifers being active during this time. And then for the last 3 billion years, so from 3.1 billion years ago to today, we call that period of Mars history the Amazonian. And during this period, it was rarer to have stable conditions for water on the surface. And so today, we especially see that water is only stable as ice. And we see this at the poles most frequently, even by looking through a telescope. But the environmental conditions on Mars do change even over the course of a year. And so Mars is somewhat Earth-like in that it has a similar length of day, and it also similarly has seasons. And the reason it has seasons is because of its obliquity, or its tilt. So currently Mars is tilted about 25 degrees, and by comparison, Earth has a tilt of about 23.5 degrees. But in the past, the tilt of Mars has varied all the way from having no tilt at 0 degrees to a very sideways tilt at 60 degrees. And this causes major changes to the climate. We see that as the obliquity changes over the years, in this case over the last 20 million years, so too does the pressure fluctuate. And results from the MAVEN mission have predicted that pressures could have been much higher, even as high as maybe 100 or 500 millibar, so much closer to Earth pressures in the past. So we wanted to design an experiment to investigate how sediment flows on Mars vary over time, from the Noachian era all the way till recently in the Amazonian. And specifically, we're asking how rheology and morphology are going to be affected by the composition of the sediment. So for example, if there's any clay included or salt in the sediment composition, and how much water content related to the Mars regolith simulant there is. And then also how rheology and morphology would be affected by the environmental conditions. So how does the Mars environment shape how these flows look? For example, by changing the atmospheric pressure or surface temperature, would we see different phenomenon? And so to do this, we utilize the Mars Chamber Facility at the Open University. And this is the chamber here shown on the right that was the same chamber used in those shocking experiments, that is Bradshaw et al. 2020 A and B. So here is an image on the right inside the chamber after one of our experiments. And you could see that there are several cameras. There are 3 video cameras which capture views from the top, from the side, and from the front view of the flow. And so we could watch these videos over and over to capture small events that happen within the experiment. We also have photogrammetry targets, and those are the little black pillars with the white circles on top. And these are later used to construct digital elevation models of the surface expression of the flow. We made several changes that are different in the Bradshaw et al. 2020 papers. So firstly, we decided to incorporate a blender, which you can see in the image on the right, and this is remotely operated. And what this does is it allows us to make sure that the sediment is homogeneous before being poured, so that the heavier grains don't settle out from suspension and the mud is homogeneous when it flows. We also created our Mars mud in a slightly different way. We did this by mixing deionized water, so water with no other components or salts added, just water, with Mars regolith simulant. We ran experiments with several different types of compositions, a control group which was basaltic in nature, and then experiments with the bulk Mars regolith simulant, and then also different types of clays, a kaolinite or a bentonite clay. We also varied the pressure, and this allowed us to simulate Mars' current conditions and its past, and also to compare with Earth pressures as a comparison. Here we see two of the main compositions that we tested. On the left, we see our control composition, so we call that Basalt 1. And on the right, we see MGS1, which is a Mars global simulant. And this was made by the Exolith Labs. And so we bought this simulant and also a version of it that did not contain extra additives. And so as you see on the left, the basalt is just purely basaltic minerals that are crushed, whereas the MGS1 matches more of the composition of the soil as determined at Rock Nest, which is one of the sites that the Curiosity rover visited and did a soil campaign. On the right, you see our results from some of the Basalt 1 experiments. And these are shown for experiments that range from 5 millibar at the top, which is current Mars pressure, all the way to 1,000 millibar at the bottom, which is Earth pressure. And so what do we notice at 5 millibar? So at current Mars pressure, we see that a flow over a warm surface does indeed levitate. So it bubbles and it ejects sand grains because it's essentially boiling. As we vary the pressure of our experiments, so as we look down at these images on the right, which span Mars history, we see that there's a critical pressure, which is around 14 millibar. So underneath this pressure, you have boiling and levitation that are active. But above 14 millibar, this composition does not boil, and instead you have a flow that looks somewhat similar to a terrestrial flow. However, if you increase the pressure, you notice that as you go towards modern day Earth pressure, the length increases. So we measure that as the length to width ratio increases. So the flows are actually getting skinnier as you go towards Earth pressure. Below 14 millibar, the same trend is actually happening in reverse. So the flows get skinnier and longer as you decrease pressure when you're below this critical pressure. And that's because levitation is essentially allowing these lobes to travel farther. Now, for the global regolith simulant experiments, so that's not just Basalt 1, but it has other minor constituents that make a more general Mars soil. And we see that all of these experiments were longer than their Basalt 1 counterparts. We also observe the same viscosity to length relationship. As the mud is more runny, it will produce a longer flow. We also found a similar critical pressure, which we can only narrow down to somewhere between 15 to 20 millibar. So we're not sure exactly how this critical pressure for this composition would compare to the Basalt 1. But we do see that the added minor constituents that are in MGS1 that aren't in Basalt 1, so these are some salt and clay components, what they do is they lower the freezing point and lubricate the flow. And what this does is it increases the runout distance over cold bed experiments and warm bed experiments. And so what this means is that minor compositions do have a key effect on flows on Mars. So here I'll show a video of one of our experiments, and you'll see 3 different simultaneous videos from those 3 different views. And the view from above, the video on the bottom, you'll be able to see a mud flow of Basalt 1, which is over a warm bed. And this is at current Mars pressure. So this experiment was run at 5 millibar. So you notice the vigorous boiling on the side of these flows. You notice there are multiple lobes that form, and every time there's a new breakout, you get levitation as it touches a new sandy surface. Over time, perhaps the viscosity increases because some of the water has infiltrated into the soil, but you do still see vigorous boiling even now in the side of this image where the water is touching fresh sand. So now let's compare that to the terrestrial version of the same composition. So this is again the same mud, but this time with the chamber door open, so it's not being pumped down to Mars pressure. What we see here is there's only a single lobe that forms. There aren't multiple lobes. The lobe is very long and skinny, and there's no boiling, there's no sputtering, and there's no levitation. So what we think is going on in the modern Mars experiments is you have the water, which is incorporated into the mud, is trying to escape as gas. It's essentially boiling, and as this vapor is coming off, including from beneath the mud flow, it levitates the flow as the gas is trying to escape. You also see ejection of sand grains, which is, again, from this vapor which is trying to escape out the sides of the flow. Now, over time, some of the water in the mud does infiltrate into the sand bed. And what this does is it increases the viscosity of the mud that's left over. And so that mud that's left now has a slower flow rate. But when you do have breakouts, so a new lobe that forms and travels over fresh sand that hasn't been infiltrated with water yet, you again see the levitation as a new lobe breaks out. So one of the questions that we wanted to answer was, is this true? Can mud really levitate? And the answer is yes. We conducted over 40 experiments in the Mars pressure chamber, and we have more planned for the upcoming years. And we were able to confirm the two shocking results. The first is that mud flows over a cold Mars surface will behave like Pohoihoi lava at current Mars pressure. Also, mud flows over a warm surface at current Mars pressure can boil and levitate. And so what this means is environmental conditions, like the pressure and temperature during fluvial activity, are important considerations when we look at remote sensing images. And so for the past 3 billion years, Mars sediment flows likely experience these ranges of low pressures, which makes terrestrial sediment flows not suitable Mars analogs. The only cases where terrestrial sediment flows would be good suitable Mars analogs are the oldest Martian cases, which would be at the highest paleo pressures. And the takeaway point here is that when we see some flow features in remote sensing images, we should really consider multiple options if they could be sedimentary and not just lava. And so we need to choose our analogs and hypotheses wisely. Our next steps for this project are to conduct additional experiments over the next few years. And what we'll be doing is testing different regolith components, including adding salts and clays, and investigating whether there's an effect of clay type, whereas some clay types are swelling and some are not. And this could impact the flow quite significantly. We're also planning to scale up our experiments to produce larger, more life-size flows, to investigate whether the physics at this scale will be incorporated at a much larger scale. So in summary, if we are to study these sedimentary environments throughout the solar system, which often occur at extreme surface conditions, we really do need different complementary views to add to our supporting evidence. For example, if we use remote sensing alone, we might hit a brick wall, and we might be left with multiple hypotheses that could be true. So, by using lab experiments, we'll gain a better understanding of the physics, and this will help us interpret these remote sensing images, and it will help us choose better analogs and create more realistic models. Thank you.
So the question is Mars end life cycle or part of the life cycle of some of these other planets? How does it fit into that as far as habitability and places like Venus or Titan? I think they might not be on the same life cycle, those three places, but they all are unique and they all have potential. So, you know, Titan has a thick atmosphere, methane atmosphere that could be conducive to certain types of life forms. Venus has a thick atmosphere. Mars has lost all of its atmosphere, almost all of it. You'll hear just how thin during this talk. It has 6,000ths of Earth's atmosphere. So only 6 millibar on average, whereas Earth has 1,000 millibar or 1 bar. And so we think that it lost most of its atmosphere in the past because it had a dynamo that shut off in its core, and therefore the magnetosphere and protection left, and a lot of water went to space and its atmosphere has thinned. but good question. Any more? Yeah. That's a good question. The question is, what's the surface temperature range on Mars? One of my plots will actually show that. It shows pressure and temperature and what the ranges are. But it's interesting because some of the temperatures could actually be similar to Earth temperatures, especially this week. But even above freezing temperatures. But the effects of pressure are what's really important. And that's what you'll see on this, is that the phase diagram of water relies on both pressure and temperature. And so even if some of the temperatures aren't 100, 200 below, and they're more like 0 or plus 10, because the atmospheric pressure is so low, water is not stable currently. All right, great questions, everyone.
The experiment that you did where the levitation was going and everything, it was an enclosed chamber. So I'd assume like near the end of the experiment, it may not represent what's actually happening because the pressure would have changed, right? Because that water's boiling off.
Yeah, so the question is, how's the pressure change during the experiment, and does that make it inaccurate by the end of the experiment? The pressure does increase a little bit because of that water vapor. But we do have a constant log of the pressure in the chamber, and the vacuum pumps are constantly working to keep that pressure at the range that we set it at. So if we set it between 5 and 7 millibar, it's constantly pumping out to be 5 to 7 millibar. So that's one way we combat that.
Okay, thanks.
Hold it. There you go.
Is there any possibility that pyroclastic flows could be causing some of these?
Pyroclastic flows absolutely do exist on Mars all over the place because volcanoes, the igneous kind, not the mud kind, do exist all over the place. And so that is a common feature on Mars.
Okay.
So some of these results might be relevant for the physics of that as well on modern Mars. Right.
I was also curious whether the physics of pyroclastic flows might help you figure out the physics of these mud flows, but someone else got there to me before I did. I do have another question though. So you were talking about trying to isolate whether these features were mud flows or say Hohoe lava. What sort of things did these researchers have to look at to distinguish between those two possibilities?
So are you talking about in a remote sensing image, what could you do to distinguish?
Yeah, so how do you know from these remote sensing without samples whether something is likely a mud flow or whether it's lava?
Right, so that's the difficult question. If you have compositional information, so in some cases, we have really high resolution terrain models of these flows. From these experiments, this is showing it might not be useful, right? If you have inflation, if you have the breakouts, if you have the similar morphology, then that topographic information might not be useful. The visible information might show the same result now too. So the real question is, do you have compositional information? Can you tell that it's composed of basalt only and not like mostly clay? However, what if the mud flow is made of basaltic class? As we expect all over Mars, most of Mars is basaltic. So the mud itself is composed of water plus those igneous materials. So it becomes really hard and challenging, especially when dust is covering a lot of these features. Then our spectral results are all perhaps too bland. So it's very rare that we have enough.
So that table that you showed of previous researchers had done all this work, might your results and of these other research kind of overthrow some of those?
I don't know if it would overthrow the major occurrences, but with our new, so the Mars Reconnaissance Orbiter has HiRISE, this high resolution camera, and CTX, context imager. And these take really high resolution images. So we've had for the last over a decade, like some new high resolution images that we keep getting every day. And it's these types of new discoveries at small scale, I think, that people need to be careful about. Yeah.
Pictures over time. Have they, have you seen new mud flows in, let's say, the last 10 years while the orbiter is going around?
Yeah, so I would say we've seen flows. We haven't seen mud flows. We've seen flows that perhaps contain water. So these are called RSL, recurring slope lineae. And there is a debate on whether they're dry or a wet process. Are these dark streaks formed by just grains rolling down and forming, exposing a darker material, or are they wet? Is there a brine involved? So we see active features that are perhaps water-rich flow features that are active today, but those are very small in comparison. So what I was mainly talking about here are like those big aqueous systems. So we're talking about lakes, rivers, deltas, large-scale mud flows, and that all happened over 3 billion years ago for the most part, which is a long time ago, but it's the best time to look for signs of life.
And that's my question for the science of life. So NASA keeps on teasing us, oh, there's water and there's this methane and stuff like that. But if things started to go bad on Mars the same time life was only just starting here, what is your perspective on the actual likelihood of life having a foothold?
So I think my perspective would be, again, there was that very, very narrow window when the conditions were kind of like how we would want them to be from our Earth biased point of views for life emerging, right? We'd want them to be a thick atmosphere, Mars to have more of its temperature to be warmer. We want liquid water stable for long, long periods of time, a dynamo to protect anything on the surface from radiation. And that's all in the first 100 million years to maybe 500 million years. So 4.5 to 4 billion years ago. So I don't have an opinion whether life arose or not, but I think another part of your question would be, you know, is it still worth looking for signs of life, even though we haven't found it on Mars in some of these other places? And I think we haven't fully done that yet. And so I would advocate for searching some of these other types of environments that are really old before we give up on that search. Yeah, so so not the universe, but of the solar system. Repeat the question. Yeah, so the universe is 13.7 billion, right? Our solar system's 4.56 billion. So the planets formed at 4.5. And what happened at 3.2 to change Mars climate? We don't know exactly. And it's a not satisfying answer, but we don't exactly know. It could have been a big impact. It could have stripped away a lot of the atmosphere and volatiles. There could have been a major outgassing event. There could have been major volcanic history, like the Tharsis region and other things that maybe even change the tilt or wobble of the planet. So there are some big things that are under consideration. I don't think we exactly know that. Yeah. So yeah, that's a great, the question is, how do you age date events on Mars? And there's a couple ways to do that. One we call relative age dating. The other is absolute age dating. Absolute, you need the material and you're taking isotope ratios to determine ages based on certain isotope systems. And we only have a couple small meteorites from Mars. We've never returned any rocks from Mars, so it's really hard to do that. So instead, what we do is relative age dating. You could look at how many craters of different sizes have hit the surface in that area. And then you could say that this surface matches the expected impact flux rate or doesn't, and you can come up with a date that way. And that's calibrated to lunar dates. So we've done this for the moon, where we have returned samples. So we have good ages for some lunar regions, and then also crater counting dates for lunar regions. And we sort of try to calibrate that for Mars. Yeah, the
So
back.
your videos were so shocking, I had to avert my eye and I forgot. Is this cold ambient water at Mars temperatures in these experiments you're showing us?
So in the we did we did like over 40 experiments, but in the ones that I showed, it was ambient condition mud. So we'd make the mud and put it in the chamber and pump down the chamber. So the environment in the chamber and the test bed could be a certain temperature that we set, but the mud was ambient. But by the time you pump it down, it does get cooler.
Mhm.
So, but it's still around, above zero, right? It's not freezing so fast in the blender that it can't pour.
And why would such a flow start on Mars? I keep thinking of mud flows like the mud pots at Yellowstone, where it's hot water.
Exactly like that. So
it's a whole new variable to explore.
So when I say mud, what I want to say is sediment flow. So you have regolith, which is the soil or sediment, and water, right? And so that could be a whole bunch of ranges from very thick to thin. It could happen from rain. It could happen from snowmelt. It could happen in a mud pot like you're talking about, like in Yellowstone. So on Mars, we don't think that the mud volcanism has the same type of source as on Earth. On Earth, methane is the driver that brings a lot of the mud volcano material to the surface, right? And on Mars, we don't think it's because of organics or methane buried. We think it's either due to a heat source or, again, that tectonic shortening. Basically, sediments that are buried are being squeezed up.
Any other questions?
So I actually had a question in terms of when you say Mars had Earth-like conditions, and if we're comparing anything and possibility of life, for instance, in that like 3.5 to 4 billion year old range, when you say Earth-like, do you mean Earth-like what Earth was like at that same time, or what Earth is like present day?
Definitely what Earth is like present day.
Okay.
So we know our atmospheric pressure today and our temperature ranges. Of course, those fluctuated throughout time, right? Earth did similar things that Mars did on different scales. And we've had, climate shifts over and over again in the geologic record, right? So I think that both Earth today and probably Earth in most of its past.
So the reason I ask is because when we talk about possibility of life, if we're looking at life originating in the Archean period, would Mars have had similar conditions as Earth of that period if we're talking about potentially life forming on both at relatively similar times?
We don't know enough, I wish we did, about early Mars and what the climate was like and the surface conditions. As we're learning that stuff about Earth too, one would think that Mars would have a very similar formation, but we're just not sure. We know Mars lost a ton of its volatiles to space, and the MAVEN mission is actually measuring how much water was lost over time. But early Mars, what did it look like? We're not sure. The only real equation you can apply to that to compare to the rate of Earth and its change would be to look at Mars from just a physics perspective, being a smaller sphere than Earth. And being a smaller sphere, its ratio of its surface area to volume is higher. And that's part of the reason why it lost a lot of its heat faster than Earth did.
Any other questions? Let's have a round of applause. Thanks, Dr. Jake Adler.
Folks, thanks for coming out tonight. If you want to stick around for a couple minutes and help with chairs, you can. I do have one announcement. There is a group of folks, and everyone is invited who wants to go. There's a group going to the Union Grill and Tap after the meeting here to have a little social time. The Union Grill and Tap is a mile over and a mile up. It's at Higley and Baseline on the northwest corner. So Union Grill and Tap. Anyway, thank you. Next meeting is next month, February 16th. Have a good evening.